All right, it's 5:30. Let's go and get started. How's everyone doing today? All five of you. And everyone on Zoom, of course. All right, so it's week 14. So we have including today 6 more meetings together before the end of the semester. So today is going to be a lecture day. So today's the prep day before activity 7, which is going to be on Thursday. So activity 7 is all about modal analysis and harmonic response. So we're going to just do a little bit of prep. Probably this is going to be a review for a lot of you. We're just going to be reviewing concepts of vibrations, resonant frequencies, and harmonic moods. And so these are hopefully all concepts you've seen before in previous classes. We're just mostly just kind of review before, just so that Thursday's activity makes a bit more sense. Okay. So I don't expect the lecture today to take up the whole time. I probably say that for all the lectures remaining. So remember, a lot of the time that we have left in the class is open office hours for you guys to ask questions about your final project. And I've been getting a lot already actually too. So a lot of people working on their own geometries, questions about the project. So definitely keep them coming. I know this is kind of crunch time for you guys. So I want to be as available as I can. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go and get started. Okay, so like I just mentioned, activity 7 on Thursday is all about modal, what we call modal analysis and frequency response. Okay, so what is modal analysis? So modal analysis has to do within the realm of structural vibrations, right? Now we talked about vibrations a little bit when we went over dynamic analysis. So what we say is that when you're looking at the dynamic response of a particular object, a lot of times you're going to be looking at its at its vibrations. Okay, so today we're going to be taking that a little bit further. And actually using the tool within ANSYS that's designed for frequency response analysis. Okay. Let me start with this. So, every object, every physical object has something known as its resonant frequency or its natural frequency. Every physical object. Doesn't matter how big, how small it is, how stiff, how pliable it is. Every object has a natural frequency. Okay. Now that natural frequency has a couple consequences. Okay. So the first consequence, the one that we primarily focused on with activity 5, has to do with the fact that when you provide some kind of external stimulus or some kind of external force, usually some kind of impulsive force, the object will naturally vibrate at that natural frequency. So, the natural frequency has a lot of, applications in what we call impulse response. Okay. So I think the easiest way to visualize this is, and we're going to be using this example a lot today, is if you look at a guitar string. So if you look at a guitar string, so a guitar string, is nothing more than just wire or some kind of string that's held taut. And so, there's a natural tension within the string. Okay. Now, when you play guitar, at some point you're going to be plucking these strings, right? And so when you pluck a string, right, so you take your finger or guitar pick, and so you're going to, pull on the string in a perpendicular direction and release it. Okay. After you release it, the string, if you really look at it really carefully, is going to vibrate. Now, initially, right when you release the string, it's going to vibrate at a range of different frequencies, but eventually all of the higher mode, we call them the higher modes, will dampen out, and the guitar string will play just one frequency. And the one frequency that the guitar string will play at is its natural frequency. Okay. So later on, we're going to see that this natural frequency is a function of the geometry of the string. It's a function of tension of the spring, as well as the type of material. Okay. But the reason guitar strings work, and the reason why musical instruments just work in general, is that we take advantage of the natural frequencies of these objects, and we tune them in a way so that the natural frequencies are pleasant for us to listen to. So they end up being frequencies that are very melodic, very nice sounding, and so that's how it's music. Okay, so that's one aspect, or one I would say aspect or consequence of the natural frequencies that you can determine the impulse response. Okay, that by itself is usually not that interesting. Not that music is not interesting. Music very interesting. But from an engineering point of view, oftentimes we're interested in structural design, failures, factor of safety, things like that. So when you're talking about vibration like this, it's usually not of extreme engineering interest. Okay? The other application that we have for the natural frequency is due to a concept called resonance. Okay? Now, with this in mind, that every object has its own natural frequency, what you can do is you can take that natural frequency and basically provide external forcing with the same frequency as the natural frequency. So if you provide external forcing that's oscillatory in nature that has the same frequency as the natural frequency, you can cause resonance to occur. Okay. Now, resonance is very interesting, and usually you do not want it to occur. Usually, resonance is something bad that you that is you want to avoid in your structural design. Okay. Let me give you, I think, the easiest way to visualize resonance, which is swinging on a swing. Okay. So hopefully everyone has had experience with a playground swing at some point in their lives, right? So in its essence, a playground swing is nothing more than just a mass that's tied at the end of a string. In other words, it's the pendulum. So we have basically, our swing set here, we have our mass M. This is our swing. But, it's a mass at the end of a string, basically, right? Now, this setup here, this swing has a natural frequency at which it likes to, swing back and forth, right? And so if you were to take this, swing, right, and pull it all the way up here, okay, and release it, and from there you can observe the back and forth motion, right? There's a natural frequency or natural cadence in which that back and forth motion will like to occur at. Right? So that's essentially what we observed in point one above, right? So every object has its own, natural frequency at which it likes to, vibrate at or oscillate at, just natural, without any external force. Okay. Now, if you've been on a playground swing before, everyone is, at least somewhat, in concept familiar with the technique to maximize your swinging distance, right? And so if you're on the swing as a kid and you wanted to, go higher and higher, right? The way that you would do that is that you would use your own momentum and try to, kick your own momentum in time with the swing, right? So how would you do that? So to maximize swinging distance, right? So we're treating kind of a playground thing as kind of like an engineering problem, right? What you would do is that you would use the momentum of your legs to help, add external force to your swing, right? And so what you could do is right when the swing is at kind of the zenith here, right? When it's kind of at the bottom, right? What do? So you take right when the swing's at the bottom, you kick your legs forward to kind of capitalize on that forward momentum. So you try to kind of, push yourself forward with the swing using your legs. Right? So that's when the forward momentum or forward velocity of the swing is at its highest. And so you kick your legs out, you provide some additional external force to kind of capitalize on that swing. Okay. All right. Then what do? So after you swing forward, right? Eventually you're going to swing back, right? And then when you're swinging back, right? You're swinging back, your motion is going in the opposite direction. What do at that point? At that point, you kick your legs backwards or you tuck your legs in to try to provide some additional momentum in that direction as well. Okay. And so you do this repeatedly, you do this over and over again, and eventually, you're going horizontal and your mom is worried sick about you, right? So that's an example of resonance, right? So with this example here, we're providing some additional external force that's timed perfectly to match with the natural frequency of the playground swing. Okay. And you can do this, and you can do this, without, with a friend as well, right? And so, if you're friend was sitting on the swing and you wanted to help them get higher and higher, right? And you provided some additional push. When did you apply the push? You apply the push right when they're at the bottom, when their forward momentum is the highest, okay? So that's the idea. And so, if you were to apply external forcing that's right in time with the natural frequency of the object, you can cause the deformations, or you can cause the swings in momentum to be higher and higher and higher, right? In theory, if you're providing these forces at the perfect times, there's really no limit to the amount of deformation that you can get up until you reach the physical limitations of the object itself. Okay. And so to put kind of an exact definition on resonance is the gradual buildup of increasing magnitude of deformation that result from applying forcing at the natural frequency of the object. So even very complex structures like buildings, cars, airplanes, they all have a natural frequency. And if you provide forcing at that frequency, then usually bad things will occur. So the reason you want to avoid this is that as the deformation builds up more and more, eventually what the ultimate kind of consequence of resonance is usually structural failure. Which is usually bad. Usually you don't want structural failure in your engineering structure that you're designing. So whenever you're designing a structure and you know that there's a possibility of some kind of oscillating load, then you have to be aware of the natural frequencies of the object and kind of design around it. And you'd be surprised that there's a lot of sources of oscillating external forces that our engineering structures are exposed to. Okay, so for activity 7, the one that we're going to do on Thursday, we're going to be looking at a gearbox in FEA, right? And so anything that's sitting on an automobile, you need to be aware of the natural frequencies, because there's a lot of oscillating loads that are going to come from the engine, right? So the engine is constantly kind of rotating, kind of providing these kind of back and forth motions, and so you want to make sure every structural component of your car is not going to resonate with the RPM of the engine. Okay. Same thing with the building. So with the building design, there's quite a few sources of oscillating load, and so the first one, especially for us that live in California, is earthquakes, right? So earthquakes, not a super common occurrence, well, California, but you want to make sure that your building is going to be resistant to the frequencies of earthquakes, so you won't get resonance and complete failure of building. But even besides earthquake, there's also wind loading, right? So anytime you have a wind force that's going to be placed on a large object like this, it's going to be providing some kind of mutter effect that's going to provide some oscillating load that can also cause some issues for certain buildings. Okay, So what we're gonna do on Thursday is we're gonna use the tools within ANSYS to not only look at the resonant frequencies of an object, but learn how to actually use that information to help with the design. And also test for resonances. Okay. All right, any questions on this so far? Okay, all right, so to kind of illustrate these concepts, let's go back to our guitar string and talk about resonance in string. Right, so we're going to use this argument to discuss, what are some important factors, or what are the factors of a structure that affect its natural frequency. Okay. So if we look at our string again, so let me go ahead and draw the figure here. Okay. We have our string. It's fixed on one side, so we have a fixed support on one side. The other side, we are applying a tensile force. Right, so the purpose of that force is just to make sure the string is completely taut. All right, and then the other thing we know is we know the length of the string. And we also know its density. But just to make our equations a bit more convenient, we're going to define our density in terms of a mass per. So that's why I'm using kind of a weird symbol for density. So density normally is rho, but rho is usually mass per volume. But since we want to keep our equations a bit simple, we're just going to do a mass per length. Okay. You can easily get the mass per length density. Just take your mass per volume density and just multiply by the cross section. Okay. So with this simple geometry, there's actually a straightforward equation where we can compute the natural frequency. The natural frequency of the string, we'll call it Fn, 2, 1 over 2L, multiplied by square root, T, divided by the mass. Now, this equation is not something that we're going to be using, right? So we found very little equations in this class. But the reason I bring up this equation is just so that we can kind of talk about different aspects. Okay. Okay, and I want to talk about it from this perspective. And so, we're going to use this equation to talk about the general characteristics of a structure that affect its natural frequency. Okay. Because for most structures are going to be too complex for us to have an explicit equation like this for the frequency. That's part of the reason why we use ANSYS for it. But even then, even when we have a tool like ANSYS, it's useful to talk about what factors affect the frequency. So if we have to modify it or we have to design around it, we know what aspects of our design that we can change. Okay. So the first factor here, that's probably the most important, is the geometry of the structure. So obviously, the one geometrical factor that we have in our equation here is the length, or one-dimensional string. That's the only geometric factor that we have. But also things like its cross-sectional area, its total volume, its surface area, the fillets, the the radii of the fillets, things like that. All of these geometric factors, all of them will affect. So usually, if you need to adjust the natural frequency of your structure, the first thing you're going to change is the geometry. Okay. And actually, if you look at the equation here, right, you look at our three parameters. We have length, tension, and the density. Okay. The geometrical factor, the length, is the only one that's not underneath the square root, right? So that tells us that the dependence of the natural frequency on geometry is much stronger than the other factors. Okay. Okay, so geometry, first thing that you're going through. All right, number two. Oh, and by the way, and you kind of tell from that equation what kind of dependence the magnitude of the geometry provides. Okay. So since the length here is in the denominator, that tells us that bigger objects have smaller natural frequency. So that's kind of important to note as well. Okay, number two. Number two, let's look at the material properties. So the material properties in this equation is represented by the density, right? So the fact that density shows up in this equation shows that the properties of the material are going to affect the natural frequency. Okay. But it's more than just the mass, and so mass density obviously plays a role, but also things like its like a Young's modulus, its Poisson's ratio, whether you have a nonlinear material, all of these things will also affect it. So you can see from this equation that, just like the geometrical factors, the mass is also in the denominator here. So, the more mass or, the higher the density of your object, the lower the natural frequency. Okay. Okay. So that's the second factor. Now the third factor is actually kind of interesting. It's something that we've been handling throughout this entire semester, but we haven't thought of it in this way. Okay? Now the third factor has to do with the tension. That's the last factor that I've circled there. But the way that factors into a general structure is through an effect that we call pre-stress. Okay. So, a concept that we're all familiar with is that when you have a structure in static equilibrium, when you apply external forces, there has to be some internal stresses like equivalent stresses that develop to keep the object in static equilibrium. Right? And so, what's interesting here is that based on how that stress distribution kind of propagates through your structure, that also plays an impact on your resonant frequency. Okay. So when we do the activity on Thursday, you're going to see all three of these factors play a role. And so you're going to see what happens, with the geometry that we have, material, see how that affects the natural frequencies. And you're going to see kind of the difference between, when you have pre-stress versus no pre-stress, how that affects your structure. All right. So these are kind of the three main factors to look out. Any questions on this so far? Okay, good. All right, so the next concept that I want to review is this idea of the harmonic modes of our structure. Okay. All right, so far, we've established that every physical object has a natural frequency. It turns out that, when an object is vibrating at its natural frequency, there's a particular shape or particular, what we call mode of deformation that occurs when the object is forced at that. And so what's interesting is that, this mode is always going to be expressed, right? So there's always a way that, our structure is going to favor its deformation when it's forced at its natural. Okay, so let me give you an example with our string. Okay, so for a string, the first harmonic mode, something like this. So you can see we have kind of one prominent peak of our string that's occurring right in the middle. All other parts of the string are going to be performing according to that. Okay, so if you pluck a string and you actually visualize the vibrations, it's going to look like this. Right? Now, what's interesting is that an object actually has additional natural frequencies. So there actually, well, I guess the best way to say it, there's one natural frequency, and then there's also additional modes that all spawn from that natural. So beyond the natural frequency and the first harmonic mode, every other resonant frequency is going to be higher than that first. Okay. So the reason, a lot of times we're interested in the natural frequency, the first harmonic mode is that's the first time that resonance can occur. Okay. Usually you're not going to get to the higher order modes unless you have a structure that's vibrating that quickly. But it's always good to be aware. Okay, so the easiest way to illustrate this is in our string, right? And so we also have the second harmonic mode as well. Now, what's interesting about these higher order harmonic modes is that they each have their own distinct deformation pattern out as well. Okay, so for example, for the second harmonic mode, we no longer have just one peak. We actually have both a peak and a valley. So actually look something like this. And this is when you force the object F2. Right? So F2 is going to be higher than the natural frequency of the string. And actually for a string, which is a one-dimensional object, our second harmonic mode is actually quite simple. So the second harmonic frequency is actually just double that of the natural frequency. Fn, remember, Fn here is our natural. Okay, now we can go beyond this as well. Look at the third harmonic mode. So this one looks like the following. And this occurs at F3. Where F3 here is, 3 times our natural frequency. Okay. So it's important to be aware of the higher order modes as well. You're not just looking at just the natural frequency for an object. You also need to look at its higher order modes. Now, for a one-dimensional object like this, the higher order modes are easy to determine. You just take integer multiples of our. But for two-dimensional objects, three-dimensional objects, the higher order modes are actually a bit more complicated. So what you're going to see is that on Thursday, we're going to find the first 6 or 10, I think it's 10 harmonic modes for an object. They're not going to be integer multiples of each other. That's a question I always get asked when I do this activity. Why are the frequencies so close to each other? Well, when you have 2D and 3D objects, your resonant modes and your resonant deformations can go in all different directions. Okay, and so the higher order modes, you can think of those as deformation modes or resonant frequencies that occur in different directions along the object. So for example, so let's say that we have kind of a triangle ramp here. So you may observe that the lowest natural frequency might be in this direction. But we're also going to observe a mode in this direction as well. 2, and there might be a mode in this direction as well. Right, where F2 and F3 here are not integer multiples of our natural frequency. right? So what you're going to be able to do in ANSYS is, you're going to be able to determine what all these natural frequencies are, and you're going to be able to observe the deformation mode of this that Okay. Any questions on this so far? Okay. All right. So that's pretty much all the background information, right? And so it's important to be aware that every object has a natural frequency, and what happens when you force an object at the natural frequency, and also about this idea of the higher order. Okay. So I would say that's kind of the bare minimum in terms of the background information. For the rest of the class today, I want to talk about the specific features within ANSYS that allow us to interact with these and analyze these features of our frequency response. Okay, so there's two main tools in ANSYS. One that's going to be the focus of the activity on Thursday, and another that I'll probably go over as well, but there's a separate handout. Okay, so the first tool that we're going to use in ANSYS is something called modal analysis. Okay. So modal analysis is a tool within ANSYS that we can use to very quickly and very easily compute the natural frequencies and the harmonic frequencies of a physical structure. Okay. All right. And you're going to see that it's going to take more time to talk about modal analysis than it is to actually run. So it's actually very straightforward to run. Right, so all you need is a CAD file, which is given. And the other thing that you need to make sure is that there are enough constraints on your geometry to prevent any kind of rigid body motion. Which we've got a ton of practice doing already. Because if you're going to do a static analysis, you need to prevent rigid body motion. And so you can think of the setup for modal analysis as very similar to that of static structure. You don't even have to put loads on the structure. So loads in this case are optional. But if you do add loads to the structure, just be aware that it is going to change the natural frequencies because it's going to change the state of pre-stress within your. So we're actually going to try it on Thursday with loads and without. Okay. So in fact, the setup for a modal analysis is so similar to that of a static structural, you can actually link them together. So actually a very kind of common way to use this is to start with a static structural simulation. And so you run that simulation, you make sure that there's no material failure, and then you link a modal analysis to it to check for the residence. Okay. And so what this will do, if you link your static structural analysis to it, it'll directly link or directly import your mesh and your boundary conditions, which you're going to use for both. Okay. Okay. So that's all the inputs. And so, you input your CAD file, you put a mesh on it, you put constraints, loads are optional. Okay. And then what you do from there is you just hit go. And then from there, ANSYS will give you a list of the resonant frequencies within the object. And that's it. That's that's modal analysis right there. So you set up the mesh, you set up the boundary conditions, you hit go, and then you get your resonant. Okay. A lot of times that's the goal, and so that's what you get from it, and that's good. But of course, there is more that you can do with this. Okay. So the first thing that people usually do is that for each of these resonant frequencies, usually you want to see what the deformation mode is going to look like for that frequency. Okay, and then you can use these results. You can use the results from the deformation modes to improve the design of your structure. Okay. Now, I want to caution you for one thing, though, that when ANSYS shows you these deformation modes, it's going to show you the deformation modes in a way that's very similar to the deformation plots that we've done before. So it's going to show you the colors on your object. It's even going to simulate the deformations for you. Okay. It'll even tell you the magnitudes of the deformation. But the important thing to note is that this modal deformation plot is not true deformation. Okay. So these plots, these deformation modes are only there to show you the shape, the relative shape of the modes themselves. But the actual magnitudes or the actual units for the deformation, those are not to be believed at straight value. So those are only there just as placeholders to show you the relative deformation. So it's confusing. That's probably the most confusing thing about modal analysis. Don't trust those deformation values because we haven't actually applied any force yet. So all we've done here at this point is we've computed the natural frequencies, but we haven't provided any kind of oscillatory moding yet. Okay. So don't be fooled by those deformation values. Those are not true deformations. Those are only there just to illustrate to you the shapes. Okay. I'll emphasize this again on Thursday, but someone always asks if this is the true deformation. It's not. Because if you look at the magnitudes, it's a little bit alarming to see how those magnitudes are. But yeah, those are not true. Okay. Okay. Now this information is useful though, because they can tell you, which directions or which ways that you can strengthen or improve your structural design. All right, so generally speaking, if you look at the deformation modes for the lowest natural frequencies, right, and you try to provide additional structure or additional additional mass or strength in that direction, then it's going to lead to an overall improvement of the design. Okay? Let me give you an example. I think the easiest way to illustrate this. Okay? So let's say that we have a table. All right, so let's say that we simulated this table within ANSYS and we found its natural frequencies. Okay, and then what we saw, right? So after we performed our modal analysis and after we viewed our first deformation mode, right? What we saw was that the table is going to deform like this. In other words, our table is going to be deforming left to right in this figure. Okay. Right, so the first deformation mode shows a very clear preference or very clear direction in terms of which way it's going to move. And that's going to tell us which way the your structure is going to collapse if resonance were to occur. Okay. All right. So if we were to improve this design, we can tell from this result here that our design is weakest in the left and right direction when we're talking about frequency. Okay. So what if we add additional structure in that direction? What if we take our design here? And what if we added some additional support beams in that? This. And same thing on the other side as well. Okay. So that's one way that you can improve the design of your structure very quickly, very easily, based purely just from the modal analysis of the structure. Okay. All right. Any questions on this? Okay, so one last thing that I want to go over. So usually I skip this for my undergrads, but because you guys are my grad students, I do want to cover this on Thursday as well. You can take the results of your modal analysis and actually feed it into another tool within this called harmonic response analysis. Okay. So far, all we've done with the modal analysis is we found out, what the resonant frequencies are. and what the deformation modes actually look like. Okay, we haven't actually applied any kind of oscillating forces to our structure at all. So in a sense, we actually don't know, what the actual magnitudes of the deformation be, right? So it's one thing when you're designing a building and you find out what the natural frequencies are, right? It's another thing to actually simulate an earthquake on your building to see if your building is going to collapse or not. Okay? So that's the idea with harmonic response analysis, is that it allows us to apply these oscillating loads to see what effect on the structure is. Because if we applied those oscillating loads, then we will actually get to know what the magnitudes of the deformation. Okay. So that's the idea with harmonic response. And so, hence the name response. And so with harmonic response, you can apply these oscillating loads, and you can actually do it over a range of frequencies as well, which is pretty useful because a lot of times when you're encountering an oscillating load out in the wild or out in the real world, there's no one frequency at which it vibrates. Usually it vibrates at a range of frequencies. Okay, so the main benefit of using harmonic response analysis is that you can specify the magnitude of an oscillating load as well as a range of different frequencies at which you want to test it. All right, and so at that, when you do that, ANSYS will simulate the response for you and show you the results as what's called a spectrum. So you might have seen a spectrum plot at some point before, okay? But it looks something like this. Okay. So on the horizontal axis for a spectrum plot, you have a frequency. Okay. And so the spectrum plot is basically going to tell you the magnitude of the deformation or magnitude of the response as a function of the forcing frequency. Okay. All right, and so usually these spectrum plots look something like this. And so there's going to be a few distinct peaks, right, where there will be certain frequencies at which the response is going to spike, and these spikes correspond to the natural resonant frequencies Okay, so that's the harmonic response. So that's usually one way to kind of take it a bit further, where if you have information of, what the frequencies of the loading are going to be. So let's say that you're designing a part for a car and you know the RPM of the engine, right? Usually you're going to want to apply a harmonic response analysis within the frequency range of the RPM of the engine. Okay? That way you can actually quantify, right? So these peaks, right? Unlike before, where with the modal analysis, you can actually treat these peaks as true deformation values. Or you can look at other quantities as well, not just the deformation. So I use deformation just because it's the easiest to visualize. But you can also look at things like the equivalent stress as well. And so see how the equivalent stress, how that's going to be when resonance occurs. Okay. All right. Any questions on this? Okay, all right, so that took a bit longer than I thought, but that's all I got for today. So I'll stick around for the next, 15, 20 minutes. So if you have questions on your project, I'll go around and answer them. But if not, thank you guys for coming today. When we come back on Thursday, we have our next ANSYS activity. Modal analysis is quite popular for the final project, just because naturally, a lot of you guys are doing structural analysis for your final project. So, modal analysis kind of lends very naturally to that. So I think, hopefully there's going to be a lot of interest in that. But yeah, if you guys are heading out, then I'll see you guys on Thursday. Yeah.
I thought maybe the impact factor, like impact analysis, and also the analysis.
Yeah.
But it's all like a talk of
Yeah. I'll do that further.
for the impact factor, like impact analysis, and what kind of situation are you going to put the analysis, the data, or
You good? I think probably more common maybe like you just drop the case. You can see how it behaves when you hit it with a camera as well. Yeah, both of those are.
I just want to ask, I don't have like quick geometry or any other thing yet, but
No, I think that's a good. Yeah, I think that's a good approach.
can I take geometry from internet or?
Yeah. Yeah, you can do that. So if you find one on GrabCAD that's similar. Yeah, then that's perfect. So a lot of people actually use it for. Just be aware that on GrabCAD, the format is consistent, so you have for different. So if you have trouble with that, just let me know. Yeah. Yeah. Yeah, that's really weird. Actually change the position. Keep in mind.
What would you consider a good mesh convergence test? Like how many elements would be like sufficient enough?
It depends. So it depends on your geometry. So what I'm looking to see is that hopefully the mesh convergence plots start kind of plateau.
Okay,
Now it's not gonna happen for everyone because especially if you have a more complicated geometry. So I would at least like to see you run maybe like 6 or 7 different tests. But if the plot's not flattening out, you're just gonna max it out as much as you can.
okay,
Yeah, and you just mentioned in the report that true convergence is probably
Higher.
more elements,
Okay.
but this is the best that we can do.
and what do you consider a good mesh size?
It
Depends also-
Yeah, it depends on the geometry as
Okay.
well. Yeah. Yeah, I would just go based on the number of elements and then you can adjust your mesh size. I think because if you're using the student version, the maximum is like 64. If you're using the lab computers, I think it's a bit higher, then you can push it on 80. So try to get as close to that as you can. If you're not getting converted, it may convert before that. So if it converted before that, then just use it.
Okay, if I have any questions about the conversion, I'll let you.
Of course, yeah.
Thank you.